What I will show you today is that actually we did some progress, and the progress can help in better understanding society and make it smarter and make it less risky. And I will show you some of the risks that we have in the society today, which is related to the fact that we have not only networks, as we see here, but networks of networks. Networks of networks mean that networks do not function by themselves. They need support from other networks like electric grid, need to support of communication, transportation services. And the model that we initiated in 2010 is actually working very well to understand catastrophe events in infrastructure because of the dependency between the network. Actually, we have two types of links. One is the connectivity links, which are the black links in the network, within the network, and the red links, which are the dependency between the networks. And the theory was given in the paper of number 1 here, which is Nature 2010, where we developed it analytically. How networks depend on each other and what are the features. And this is what I'm going to show you today. And the main feature is because of the dependency, you do see cascading failures in one network lead to failures in another and back to the first network. And because of the cascading failure, instead of phase transition that we see here, the continuous transition that we see for single network, single means like the Poisson one or the scale-free, we see a continuous phase transition, which means that if you remove randomly or attack some nodes, the network fails continuously. You can remove more and more, and the network still survive. However, when you have the dependency, what happens is that you have a cascading, and you reach a point at which the cascading start by itself and do not finish until the network collapse. And this is why we have the abrupt transition. You see the abrupt first order transition, it jumps. And this happens a lot in real life. But what I want to show you today is that I wanted to test the theory on some experimental. And of course, I cannot make experiments on electric grid, on communication. Nobody will allow me to do it. So I went to the physics lab, and I will show you today two experiments, one on superconductors and one in lasers, which show exactly the same feature that I expect in the theory of a network of networks. So let me, so this was not new, that networks depend on, this was almost 10 years before my paper. We see Rinaldi from Italy, from Florence, I think from Florence, and he showed this beautiful picture, how systems depend on other systems. All systems actually depend, oil, electric, power, and they depend on each other. So if you have failures in one system, it leads to failures to the other one and the other one. Actually, we know our body is the same. All systems in the body depends on other systems. So we need to make a theory of network in order to understand even our body. But it seems to appear in many systems that, as I will show you some examples, but you can imagine many examples in which it appears. So an example, and this I think I owe to, Vespiniani is not here, but I think he was the referee of our paper in 2010. I'm not sure, I don't know if he told me, but he wrote a comment. He said, okay, your theory is beautiful, but give me one example in which it appears in infrastructure or in reality. And then luckily we found this example in Italy, from his country. Vespiani is from Italy, and we found that in the blackout in Italy in 2003 was caused because of the interaction between network. And this I did not say, it's the Rosato studied this in 2008, 5 years later, and he realized that what happens is that the two network, the communication that controls the power grid, and the power grid, there were failures, cascade of failure between them, which you can imagine here, failure in the room led to failure in the communication system, and the communication system lead back to failures in the power grid, because a power station cannot function without communication. It stops to function. If it doesn't have communication, we have to transfer the electric. And then what happens is that finally Italy broke down to two pieces, and they shut down the whole, and this happens in many. The
most news in the morning.
And I'm showing you now.
American morning.
Also,
6 a.m. Eastern.
The game was sponsored by the Bipartisan Policy Center, and it simulated, as you said, a massive cyber attack on the U.S. Former government and business leader played the parts of top officials. There was a fake news channel. The scenario was entirely fictional, but the issues could not be more real.
Up to 20 million and counting of the nation's cell phones have stopped working so far today in what officials claim is the largest communications crisis in the cell phone era.
The reason? A cyber attack.
this was done by CNN. I didn't do it.
There's one overarching question.
Is this an act of war, not a criminal act?
The infected smartphones show a video of the Red Army, raising speculation the Russians are behind the attack. Meanwhile, the crisis expands.
Instances of identity theft
Cascading
and
failure.
financial fraud have increased dramatically.
Officials discuss the possibility of shutting down the infected smartphones, but government can't do it.
I'm actually shocked to hear that we don't have this authority. If this was someone with smallpox wandering through the Super Bowl, we would have the authority to quarantine them.
Can the military assist? What powers does the president have?
We are operating in a bit of uncharted territory, as you know.
The attack is traced to a server in Russia. If the U.S. shuts it down, will the Russians see it as an act of war? And is Russia really behind the attack? Then more grim news. The internet is infected. The power
Cascading
grid is
failures that came
We
to
are
other
also
systems.
now receiving alarming reports of significant and growing power outages in major metropolitan areas in the east.
Okay, this was important to show that how risky is the fact that we have dependency between the systems. One system fails, the other system also fails, and it can lead to catastrophe. So the model is very simple, that we started with a model in which we have networks. Each point, each circle, blue or green circle is a network, like you see over there. And we have a network of networks, but they depend on each other, like the picture in the right, the top right, like this picture. So, and now the question is, can we solve it and generalize the theory of single network to many networks? And indeed, when we solve a single network, this was done, as you see here, about 66 years ago by Erdos and Reini. He solved the problem and he found the analytical solution for a single network, n equal 1. N equal 1, and if found the analytical, and it's continuous. For single network, we have a continuous solution. However, when you take two network, three network, which depends on each other, what we found that the solution is generalizing the single network solution by a very small letter. Here you see n, and this n that appears in the power represent the number of networks. So when n is 1, of course, you get all the classical solution. But when n is 2 and you solve it, you see that instead of getting continuous solution, you have an abrupt solution. This abrupt solution, n2, you see it jumps. And these are the abrupt solution which made me very interesting. What happens in this abrupt solution? And what I want to tell you that I believe now, I'm not 100% sure, that what we see in nature, in technology, abrupt solution, the origin of this is what I will show you in this talk. I mean, when you have abrupt transition from one material to another, or from, we can learn from this example what happens microscopically in this system. So we have now this solution, and let me show you what happens. In one slide, you can understand what happens in during the abrupt solution. So you see here the example here, you have a continuous transition when you have the system fails. If you remove more and more nodes, it fails continuously. But when you have coupled network, you have a first order, you have a jump. And now let's look on the jump. And the jump you can see here in this picture, this is the jump. And during the jump, we can now, because we have analytical tools, it's a very simple problem. Networks are not physics, are just geometry, nodes and links. So we can do it mathematically. And we realize that during the jump, you have a plateau. It doesn't go up from up down immediately, but there is a plateau, meaning that the big component reduces very slowly during this plateau, very slowly, microscopically. The microscopic changes. This is the cascading that appear during the plateau, and this cascading is very long. It depends on the size of the system. You will see later. And during the abrupt transition, as you see, we can find that the branching factor means failure, lead to another failure, cascading. Branching factor is 1, similar to epidemics. I mean, during the abrupt transition, there is a branching factor 1, and during, what does it mean, branching factor 1? So if you look on here, if you measure the branching factor, I mean, I make a failure, and I want to see how many, I make many failures in the system, single failures, and I want to see how many failures it leads. It will lead exactly to 1 at the abrupt transition. But if I go below the transition, it's faster, and the branching factor is larger than 1. You can see it here in the eta, in the middle picture. And when you go above, the branching factor is below 1. Below 1 means that it cannot propagate. That's why the system holds. So it's a very simple phenomena that appears in, I believe, this is the reason why we have abrupt transition. Abrupt transition is exactly the case where you have branching factor 1 and it spreads all over the system. So this is the case of, and you can see here now, but if you look on it, we can find very new phenomena that never was studied before. What is the length of for example, the length, sorry. Length, how to go back, maybe I cannot go back. Yeah, what is the length of the plateau? So the length of the plateau depends on the system size. In our case, it goes like n to the 1/3, the number of nodes that you have in the system, and depends how far you're from criticality. Tau goes like PC minus P to the minus 1. This is analytical derived, and we see it in experiment very clearly. Actually, people noticed something plateau before, but they say that it's just noise or something, but they did not understand it like a phase transition. And more than that, they find also that near the plateau, near the abrupt transition, above the abrupt transition, the giant component goes like a critical exponent. That's why it's called also mixed order transition, mixed transition. And when we look on it, it does not depend on if it's a random network or even a lattice network, always we see the same phenomena. So, but this was a theory, but we could not measure it in real infrastructures. As I told you, I cannot control them. So can we prove the theory in experiment, to go to real experiments? So I went to my friend, the experimentalist in superconductivity. I told him, why not to take 2 superconductors and put them together with dependency between them. The dependency will be the heat. The 2 layers are layers in which they can transfer only electricity in each one of them. And there is an isolator, current isolator between them, but it can go between the network, and this will represent like 2 networks which depends on each other. So this is what we did, and indeed we find whatever we see in networks without physics, we see also in networks with physics. And what we see? We take 1 layer like this, and we measure the resistance. So this is superconductor. You see the resistance is 0 below a TC. For each layer, it's even different. You see the transition because the elements are different. But when we put them together, with the dependency between them, like the dependency that we had in between the networks, we see abrupt transition. So the continuous transition become abrupt, and more than that, we see the exponent in the near the transition, as I told you, is 1/2, as I showed you in the theory. You see the 1/2, both in experiment and in theory. And the understanding is that there is heat going between layer to another layer. If a superconductor becomes a conductor, so there is resistance, and the resistance brings heat, and the heat goes to the other one. And that's we have the cascading failure, like the cascading in network. Failures in one network lead to the other, and back, you have back. So the same phenomena and the same exponent here, but what about the plateau? Do we see the plateau? It took him maybe 10 years to find the plateau, and after doing this, in 2023, we published and we saw the plateau also appears here. You see the plateau in experiment. You see, when you are at criticality, you have a long plateau here, and when you are far from criticality, you see shorter plateau and shorter. And when we put it together for different size of plates, we see exactly the phenomenon predicted. It means the tau goes like n to the 1/3, and it goes like a square root IC minus IB to the minus 1/2. And we also measured, surprisingly, the branching factor. This is measurement, this figure in the right. So the branching factor here is not 1, but I told you it's 1. But it's not surprising because the two superconductors have a different resistance by a factor of 30%. So we see here the branching factor 1.3, because one superconductor becomes a conductor, but it's a bigger resistance. So and the other one is smaller. So it brings back and forth. So we get experimentally exactly the tau data that we found in the theory. So we have now one example. And more than that, when we measure the branching factor you can measure by looking on the plateau. Plateau is cascading. It means one failure leads to another one. So we measure the difference the difference during the plateau. You see, this is the equation. How a change makes the new change. Like if I'm infected, how many people are infected? And the ratio between them. And the ratio, look, is really giving me, when you are at criticality, you see it's very close to 1. When you are above criticality, it's above 1, below criticality, below. So we have a very simple explanation. This simple explanation can explain now, I believe, all abrupt transition that we see, because it's so natural to have a branching factor that makes the abrupt transition. And more than that, last year I came to experimentalists in lasers, and I told you, why not to make 2 lasers coupled? And when we do it, we see exactly the same phenomenon. We didn't publish it. This is not yet published. So, so what we see, if you have no coupling, this is the blue curve, the power as a function of current increase continuously. This is a phase transition, it's known. If you take a linear coupling between 2 lasers, you see the red line, also we don't see abrupt. But when we take non-linear coupling between them, you need a non-linear coupling. You see exactly what we saw in the phase transition of the, you see hysteresis, I didn't mention it, hysteresis, because it depends on the direction that you go. But you see this experiment here, exactly like we see in the superconducting material. And here we see, so you see the abrupt transition. When you increase the current, it goes with the red line up jump. And when you decrease the current, it goes with the green light a jump. And the exponent you see is there, giving here. Also the tau, the plateau. We measure the plateau. This is the plateau. And we see the plateau, beautiful exponent with I minus IC to the minus R. It means when you are close, it takes a long time because the branching factor is 1. So it takes a long time to reach the whole system. But when you are farther away, it becomes smaller and smaller. You can see it here in this plateau becomes smaller and smaller. So first, in order to solve problems, risky problems, we need to understand them. When we understand them, we now can make a method to avoid such coupling. And one of the methods that we discussed, we invented, was to make decentralization. What is the reason that we have this cascading? Because the network is like a central. If You are in the network, you are functioning. If you are not in the network, you're not functioning. So why not to change and to make some nodes that can function without the network? They have their own electricity, they have their own communication. And these red circles are those that we make like reinforced node. We give them extra communication or extra electricity. And indeed, when we do this, then we checked what happens to the cascading failure, and you see it's enough to give for the power grid of Europe, where you are now. You see, this is the power grid of Europe. If you give only, if you give 1%, the jump goes smaller, but if you give 2% of reinforced nodes, you avoid the jump, because it's enough to minimize minimum number of reinforced nodes or decentralization. I mean, the center is centralized. This is the reason why we have such cascading failure. So let me go now to the summary and conclusion. So we need not only AI, we saw before all day, AI solves the problem. I think AI is important, but science is maybe still more important. We need science to understand better the mechanism, what's going on. And we see statistical physics approach can lead us to understand cascading failure that happens during abrupt changes. It's microscopic phenomena that happens in the system that we didn't realize before. Now I think it's clearly realized. The new paradigm abrupt, we get abrupt because of the cascading failure. And we generalize it. I told you, instead of having n equal 1, which we studied for many years, we need to study general n network, which depends on each other. Now proving these experiments that actually it seems that we can prove that we do have the cascading failure. We can see it in the laboratory. We can see the plateau. We can see the exponents which causes them. Now, so as I told you, I do believe that microscopic processes occur in all abrupt transitions in nature and technology. I put a question mark, so because I'm not 100% sure, but I believe that what we saw is so simple and so logic that it must be true for any abrupt transition. And what I missed in this talk, there is another point which is very important: liquidation phenomena. We realize also in the theory of networks, without experiment anymore, that because of the dependency, because of the two types of interaction, you can destroy the system by making a critical size of damage, microscopic, and it will spread in the system and will destroy the system. So it means we have more risk that I did not mention. And not only this, it may be that we can, the opposite, recover the system. Recover means like our body, perhaps, if we have this type of, we are checking it now in the lung, for example, we have a collaboration, that maybe we can do, you can fix certain damage in a certain area, and this will spread and make the lung healthy. So maybe it's general. So we have other type of transition, which I didn't mention at all, but if you read my papers, you can find this, they appear in networks, but we didn't see it yet in real system because it's more complex to do it. Thank you very much.